Hey, this is going to be a short screencast on the continuity theorems. We mentioned these in class, but I'm going to say something about them, go a little deeper on a proof, and maybe talk about a slight extension of them. So sit back and enjoy. This is the statement of the continuity theorem, and the idea of the continuity theorem is building new continuous functions out of old continuous functions. So the supposition we have, or the assumption we work with, is that we've got two continuous functions, and they're continuous at a single point. So f and g are continuous at a point. And then I'll use this constant here for one of the results. So if these two functions are continuous at a point, then all of these functions are continuous at the same point. Now what we're doing in this theorem is that we're building new functions out of the old functions. Okay, so here we're making a constant multiple function. Here we're adding two functions, here we're multiplying two functions, and here we're taking a quotient of two functions, and then we're adding this additional condition that the denominator isn't vanishing. And then the fifth case of the continuity theorem has to do with composition. So this is another way we can combine functions that's unique to functions. That's part of the algebra of functions. And so the conditions for a composition to be continuous are slightly different. It's not as simple as saying the two functions are continuous at the same point. We say the second function, g, is continuous at the output of f at c. Okay, because that's going to be the input of the composition. And then we want to make sure that g is defined near that value. And so if g is continuous at f of c and g is defined near f of c, then the composition is well defined and it's continuous at x equals c as well. Okay, so what I'm going to do is I'm going to explain why a couple of these are true. But before I do that, let me just make sure that we're on the same page about some of the stuff that's happening here. So when I define this function k times f, okay, this is a brand new function, and unless k equals 1, this function is different from f. And the way we define it is that we're going to define all the outcomes in terms of the outcomes of f. So the output values of k times f are equal to the outcome values of f that we then multiply by k. So if we had a graph of a function, let's say a parabola, say this is y equals x squared. If we multiplied all the outputs by 2, what that's going to do is it's going to create a steeper parabola, and this would be the y equals 2x squared. So there are geometric interpretations to these operations, like the operation of addition and multiplication, and you probably have seen those in the past too, but I just want to make it clear to you, and because we'll use this in a moment, that when we define these new functions, like the sum of two functions, we're doing it in terms of the outputs of the original functions. And this is often called a pointwise definition of these new functions, because we're defining them using their values at each point. Okay, and that's what that means. So what I'm going to do next is I'm going to show you why these statements are true. And actually, I think I've got in this slide deck explanations for why those three are true. This one's similar, and this one you can figure it out if you spend a little time with it. And so these are mathematical proofs. So I'm going to give you an honest-to-goodness mathematical proof. So let me talk through it, and then I'll go back and make some points about it. So we want to prove that if a function is continuous at a point, and then k is a constant, then this new function is also continuous at that point. So specifically, we want to show that k times f of c is continuous at x equals c. And what that means is that this limit statement is true. And this should be familiar to you in our conversations from class, because this is an expression of the idea that a naive evaluation works. Okay, you evaluate this limit, and it's just like plugging in x equals c. So now, noting that we defined our new function here, k times f, in a pointwise fashion, we can write the following limit statements. Okay, remember, we want to prove that this limit is the same as this number. So we're going to start off with the left-hand side. Here's that limit. And that equals this limit, okay, and we're using the pointwise definition here, right? K times f of x is k times f of x. And now we're going to use a theorem that we proved or justified a while ago, and this is one of the limit laws. Okay, we're going to use a limit law that tells us that we can pull that constant out of that limit. Okay? If the limit of this f of x exists, then you can pull that constant out, which we do right here. So the limit of k times f is k times the limit of f. Now we know f is continuous at c, so this limit is the same thing as f of c. So I'll make that substitution. And then, goodness gracious, here I've got k times f of c, but that's the pointwise definition of k times f evaluated at c. And this establishes what we wanted to prove, right? We wanted to show that this is true, and we did. On the left-hand side, we've got that limit statement, and on the right-hand side, we end up with what we wanted to end up with. Okay? So that's the proof. And the key here is using the limit law. That makes all the difference. All the rest of this stuff was just definitions and moving symbols around according to definitions. What makes this proof work are the limit laws that we proved not too long ago. All right, so let's look at one more. Here's the proof of the second statement, that if f and g are continuous at a point, then so is f plus g. Okay? So let's prove that f plus g is continuous at x equals c. This means, according to the definition of continuity, that if I take the limit as x goes to c of f plus g of x, it has that value. That's what I want to prove. So noting that f plus g is defined pointwise in this way, as I remarked before, we can write the left-hand side, right? The left-hand side of the limit we're interested in. Now I'm going to use the pointwise definition of the sum function f plus g, and yes, there are parentheses there. And now going to the next step, here again is where I invoke the limit laws. The limit of a sum is the sum of the limit. Okay, that limit law theorem. And now I know that f is continuous at c and g is continuous at c, so the limit as x goes to c of f is f of c, and the limit as x goes to g of g is g of c. Okay? And then this, using the pointwise definition of the sum function, this is the same thing as the value of the function f plus g at c. Okay? So I just proved what I wanted to prove, that this limit has this value. Okay? So again, to recap, what makes this theorem work, what makes this proof of this theorem work, are the limit laws. Okay? And then I guess, to be fair, here we also use the definition of continuity. Okay? We use our assumptions here. You have to use your assumptions that your original functions are continuous. One more. Here's the third one, the fact that the product of continuous functions is continuous. So, assuming my two functions are continuous at c, and I want to prove the product is continuous at c. So this means I need to prove that that limit is true. The limit as x goes to c of the function f times g at x has that value. So we'll use that pointwise definition again, that the value of f times g at x is f of x times g of x. When we calculate this limit, right, we want to show that this limit equals that value. So we'll start off on the left-hand side, and then we'll use the pointwise definition of the product function, and then we use the limit laws. The limit of a product is the product of the limit. If these two limits exist, you can write this single limit as the product of those two limits. Okay? And then we use the definition of continuity again here to say this limit as x goes to c of f of x is f of c, and likewise this is that. And then we conclude by using the pointwise definition of the product function right here to write f of c times f of g as the value of f times g at c. And there you go. That's what we wanted. Okay. So that's how those proofs work. The proof for the fourth property with the quotient works the same way. And then the proof for the composition, you also use the limit laws. You also use the definition of continuity. You just have to be a little bit more careful with your definitions. So we've talked about in class families of elementary functions and how they're a rich example of continuous functions. Polynomials, cosines, sines, exponentials, logarithms are all continuous. Am I leaving any out? Root functions are continuous. Some piecewise functions are continuous, like the absolute value, but some piecewise functions are not. But these here are examples of continuous functions. There's other trig and other rational functions that are quotients of continuous functions. So the previous theorem tells us they're continuous wherever they're defined. So I'm going to scroll back and show you that in the theorem. So here in property 4, tangent is sine over cosine. Right? So if f is sine and g is cosine, sine and cosine are continuous functions. So this quotient is continuous wherever my denominator doesn't vanish. So wherever cosine is not 0, the tangent is perfectly continuous. Likewise for rational functions. Rational functions are quotients of polynomials. So f, the numerator, is a polynomial. G, the denominator, is a polynomial. Polynomials are continuous everywhere, so we can apply the continuity theorem and we can conclude that a rational function is continuous everywhere that the denominator doesn't vanish. So that's pretty powerful, though we can conclude that also from the limit laws. But the continuity theorem lets us recognize other functions that aren't members of these elementary families, but we can look at them and see that they are indeed continuous, like x times cosine x. That's a continuous function because x is a polynomial and therefore is continuous. Cosine is a trig function, a special trig function, and it's continuous. So by the continuity theorems, the product is continuous. The hyperbolic cosine, right? It's the average of two exponential functions. E to the x is continuous. E to the minus x is continuous. So you add them together, you get a continuous function, and so you take a scalar multiple of them, you also get a continuous function. E to the minus x squared is a composition of two functions. X goes to minus x squared. Well, the function minus x squared, that's a continuous function because it's just a polynomial. And now minus x squared is inside this exponentiated function, so it's a composition of two functions. Polynomial continuous, exponential continuous, therefore the composition is continuous. Okay, so this is a nice continuous function. And likewise, if you square a trig function or you take a power of any continuous function, it's also going to be continuous. Again, that's a composition. So the continuity theorems are really important, and this is one of the reasons they are, because it lets us recognize where other functions are continuous. And continuity is going to be a basic property for us. We want to be able to recognize when a function is continuous, when it's not continuous. And then functions that are continuous, they might have these other properties that we're going to study in this course, like differentiability. So I want to just close by saying that the continuity theorem it assumed that f and g are continuous at a point. Okay. But you can swap that out for the phrase f and g are continuous on an interval. And the same theorem is true. 1, 2, 3, and 4 go straight on forward, straight on through. You don't have to change a single thing, right? Except what we're changing here by swapping these phrases. Property 5 about compositions of functions, it's also true, but again, you have to be a little careful with the language because you're composing functions. That's a different way of putting them together. But this says if two functions are continuous on a shared interval, their product will be continuous there, their quotient will be continuous there unless you get division by 0, etc., etc. So this is an important thing to keep in mind as well. And that's it. That's what I wanted to tell you. Make sure you understand what this theorem is telling us, why it's important, and how we use it, and you'll be good to go and ready for differentiability.